So, did I start? I started. I did. Okay, so exponential functions are functions of the form f of x equals a raised to the x, where this is called the base. You know that, and this is called the exponent. And so basically, in an exponential function, you have the variable. One of the variables is the exponent, and the dependent variable is the y value, or the f of x, that you get out. All right. For an exponential function, and I'm sure you've seen these before, right? You guys, how many of you have seen exponential functions before? Yeah? No? I think you. You must have seen them last year. So a has to be bigger than 0, okay? Meaning it can't be a negative number, although you can throw like a negative number in front of the a, but a has got to be a positive number, and also a is not equal to 1, and also x can be any real number. X can be any real number. Why can't a be 1? What would it look like if a were 1? If a were 1, it'd just be 1 to the 2, 1 to the 3, 1 to the 4. So what would that look like? Yeah, it'd just be a horizontal line, right? It'd just y equals 1. So that's why it would just be a linear function. So x can't be any real number, and a has to be bigger than 0. So you've seen some exponential functions like y equals 2 to the x. And you're probably used to plugging in numbers like 2 to the 3. So then if I were to graph something like this, why is it a dotted line? I don't know. But if I plug in, let's make a little table of values. X, y, if I plug in 0 in there, what do I get out? 1, right? So I get out 0, 1. If I plug in 1 in there, what do I get out? 1 in for x, what do I get out? 2. If I plug in 2, what do I get out? 4. 3, I get out? 8, right? And so it ends up 2, 4 might look something like this. 3, 8 looks something like this. So it goes up this way, and then you can have negative numbers. What if I plugged in the number -1 down there? What do I get? Yeah, I get 2 to the -1, right, which is the same as 1 over 2 to the +1, which is the same as 1/2, right? So what happens here is with negative values, you don't get negative numbers. You just get numbers that get closer and closer and closer to the x-axis, okay? So exponential functions, they usually have asymptotes, and the basic exponential function has an asymptote at y equals 0, but it doesn't have a horizontal asymptote, okay? Horizontal asymptote at y equals 0. Now, unlike numbers that you've plugged in, nice integer values and stuff, but can I plug in a number like 0.7 or something like that? Could I do that? Yeah, you could plug in any number. So 2 raised to the 0.7, well, it's going to be somewhere in between 1 and 2, right? So 2 raised to the 0.7 power, what does that mean? Well, I'm raising it to more than the 0 power, but less than the 1 power. So I'm guessing it would be somewhere between 1 and 2. So 2 to the 0.7 would be like somewhere in there, right? But you can plug in non-integer values into exponential functions. All right. For y equals 2 to the x, and well, for most of these graphs, for y equals a to the x, you have a point, special points special points, I guess you'd call them, you would have the point 0, comma what? Always. If I plug in 0 in here, what do I get out? 1. Okay? And you would also have the point 1, comma what? A. Okay? And then you would also have the point negative 1, comma what? 1 over A. So those are some kind of special points for all of these functions. So if you have like y equals 4 to the x, right? You're going to have the point, it's always going to go through 0, 1, unless it's shifted up or shifted left or shifted right or something like that. Okay, it's always going to go through 0, 1. It's also going to go through, whoops, that should not say 1, 0, that should say 1A. I'm sorry. Okay, 1A. And it's also going to go through the point 1, comma what? 4. And it's also going to go through negative 1, comma what? 1, 4. So there's some nice quick, to get a quick idea of what the graphs look like. You could just plug in those special points and you could get kind of a good picture of the graph. So what if I had the graph, what if I wanted the graph y equals a to the negative x? Do you guys know? I'm going to get solid graph paper with some lines on the end. Okay? What do you think y equals a to the negative x would look like? If y equals a to the x goes this way, what do you think negative x does? You want me to tell you?
The opposite way.
It goes the other way. Okay? What is that? Go away. So it would be going, if y equals a to the negative x, it would look similar to that, but it would go down this way. Because basically what it's doing, if I were to plug in some values like x and y, if I plug in like 1 in here, I'm going to get a to the negative 1, which is 1 over a, right? So if I go, it's going downhill right there. And if I were to plug in like negative 1, I'd get out a to the positive 1, which would give me a. Alright, so it's going like this and this. And then again, you would also still get out 0, 1, and so on, like that. So a to the negative x would look like that. And then you could shift things around. What if I wanted to graph f of x equals 3 raised to the x plus 1? What do you think that would do to your graph? Any guesses? What is that? It's kind of like this. What does that do to a parabola if I do a plus 1? It shifts it left, okay? So this would shift it left. 1 will do. So shift left 1 unit, 1 unit. What if I did g of x? G of x equals negative 3 to the x, like that. What do you guys, what's a negative sign going to do? Think about it as transformation. So if 3 to the x looks like something like this, what do you think negative 3 to the x would do? Okay, right, it's going to be a reflection across the x-axis going this way, okay? So this negative sign reflects over x-axis. So these are just some kind of transformations. Think about, what do you think y equals 3 to the x minus 2, if I put the minus 2 not as an exponent but minus 2. What does that do to a parabola? It pushes it down 2. So basically this would be down 2 units. So what do you call that? A vertical shift of 2 units. And it would move the asymptote down, right? So if this were 3 to the x, we're looking like this, okay? then 3 to the x minus 2, it would have a new asymptote over here. It would be, that asymptote would be down here at x equals -2, and it would look something like parallel kind of to that, but it would be shifted down to. Questions about reflections, translations, all that kind of stuff. You'll see some of those in your homework. I translate this, stretch it, shrink it. Okay? Then we have the number e. How many of you guys have seen e before? E? Okay. So e is, that's called the natural, it's called the natural base. Natural base. And E is approximately, there's a button for it on your calculator. E is approximately equal to 2.718. It's an irrational number that goes on forever. 2, 8, ... Okay? And E comes from, they don't really have this in your book, but it comes from the limit as x goes to infinity. And you don't need to know this notation yet until we start talking about limits, which I think is like chapter 11 or 12. That's what E is, okay? So as this number gets really, really big, and this number also gets really, really big, you get close to this number, 2.7128. I can show you on a calculator, but so for instance, if I took like 2 and plugged it in here, I get 1 plus 1 over 2 raised to the 2. And then I took 1 plus 1 over 3 raised to the 3. 1 plus 1 over 4 raised to the 4. So you're raising it to a higher power, but you're adding less and less each time, okay? You end up getting closer and closer to that number E. And you can plug that into your calculator. Let's see, do I have my calculator? Where's my calculator? I'll show you. So say I were to put in y equals clear, and I go up here and put in parentheses 1 plus 1 over x raised to the x. And if I go to second table set, and start, let's go to, it's unasked, so that doesn't matter. So if I go second table, and I go and I put in some numbers. Where are these? Where? Anyway, if I were to put in 1 in here, I should just get 1 plus 1, right, raised to the 1, which would be what? I should get 2, right? And then if I put 2 in there, 1 plus 1/2 raised to the 2, I get out 2.25. And then if I put 3 in there, okay, I get out 2.37. And then let's put 10 in there, okay? See, I'm getting closer to some number. And then if I put 100 in there, I should get really close to E, 2.7. What did I say? It's 2.718, something like that. Okay. If I put 1,000 in there, okay, you get to, so I'm getting really close to that value for E. And then E comes up a lot when things are growing at a continuous rate. For example, interest, or bacteria, or radioactive growth, or anything like that. Because, you know, like if you think about a bank, you know, it's compounded monthly, compounded quarterly, compounded annually. Then they say compounded continuously. And that's where the number e comes into play. All right? So you should be, and graphs of y equals e to the x, it looks just like the other ones. Y equals e to the x just looks like y equals 2 to the x. But instead of going through, it also goes through the point 0, 1, right? Because when I plug in 0, but then it goes through the point 1 what? What would this second point be? 1 comma what? E, right? Because, and so that's like 1, 2.718, and 1, negative 1, 1 over e. So it looks like most other exponential functions, and it just kind of goes up quicker than 2, but less quick than 3 to the x, and so on and so forth. So just some types of problems that you might see is like sketch a graph. Sketch, is that how you spell sketch? No, sketch. Hey, that's sketch. Yeah. Isn't that kind of a cool thing to say? Yeah.
Your sketch, Mr.
Does that? What does that mean? Like cool? That's sketch. That's
No, it means like it's scary.
It's scary. Oh, I know.
Like.
Okay. Sketch the graph of g of x equals 1/2 e raised to the negative x. What do you think that's compared to? So using transformations, I'll say, and this would just be a sketch. It wouldn't. Oh, now we're always going to get hung up on that word. Okay. It's just going to be a sketch. It's not going to be the actual graph. So if I know that if this is y equals e, oh look, it even has arrows on it. If that, but I don't want to do that because so if, let's say that this is y equals e to the x. What's this thing going to do to it? The 1/2 in front.
Impressive.
It's going to squish it, right? It's going to make everything lower. So instead of this being the 0.01, this would be the 0.01/2, except now it's going to come down from which direction? From the left side, right? So if I were to graph y equals e to negative x, it might look something like coming down this way and then going through 0, 1/2, and going something like that, and probably be flatter and wouldn't go out as steep as this one. Okay, so that one might look like that. Questions about transformations and things? All right. So then we have, so I did tell you that these things, I'm not going to do all of these different formulas and stuff, but there are lots of applications with e and exponential functions. So applications. So say I have, and the first one where you're going to see for compound interest formula looks like looks like A equals P times 1 plus R over N raised to the NT. Have you guys ever seen that formula before? Okay, I teach in Algebra 1, so I know. See, they don't learn it, but I teach it. Okay, so this over here, that's the principal. So if you're investing money in a bank account, that's how much, that's your original amount, okay? This is the, just kind of, that's the amount in the account after a certain period of time. And account. This is your interest rate. And that would have to be as a decimal. So if it were, your interest rate were 7%, that would have to be 0.07, right? And n is the number of times being compounded. Number of times compounded per year. And that's the same number that goes up here. See? And this is the number of years. This is here. And so say, for example, if you were to invest $9,000, so invest $9,000 at 2.5% compounded annually. Compounded what did I do first? First I did compounded annually, quarterly, and continuous. Compounded annually, quarterly, and continuously. Did I do monthly too? I don't think I did monthly. Continuously. How much money would you have? How much in account after 5 years? Could you do that? Have you done that before? What do you think there, Jeff? So all you do is you plug in A equals, P is always 9,000. 1 plus 0.025, and quarterly, so this is for quarterly, you divide by 4, and then you go 4 times 5. So in other words, you're taking 2.5%. So you think like, oh, they're earning, like you're earning 2.5% compounded quarterly. Oh, that's really great, you know. But it's not really that great because you're only getting 1/4 of 2.5%, right? 4 times a year. So over 5 years, how many times are you going to compound that amount? 20 times, right? So you're going to get 1/4 of 2.5% 20 times within your 5 years. And I did this beforehand on the calculator, and I get $10,182, $10,182.67. Okay, that's if you compound it quarterly. Oh, sorry, I didn't do annually. Annually, I should have started with annually. That's just kind of like straight interest. 9,000 times 1 plus 0.025 divided by 1 raised to the 1 times 5. Okay? And if I do that, I get that that's about, that was the wrong answer for the first one. This was annually, sorry, $10,182 about. Quarterly, it comes out to be a little more, but not that much more. $10,194 about. Okay, so if you compound quarterly, that's better, right? But you're only making how much more? $12 or something like that. And then for continuously, you use a different formula. For continuous compounding, it comes out to be A equals PE raised to the RT, like that, where R and T are the same things they are in the other thing. And so you think, well, if I compound it 365 times a year, or monthly, which would be 12 times a year, or continuously, it's not that much. It doesn't come out to be that much different. So in this case, I do 1,000 times E raised to the R, which is 0.025 times 5. So essentially, you're raising E to the 1.25 power, and then multiplying by 9,000. And if you do that, you get $10,198 and some amount of cents, and 34 cents. Okay, and so the difference between compounding quarterly and compounding continuously is only $4 or so. Okay, even though you're compounding, instantaneously, but you're only compounding a very small amount. You're only getting a very small amount of interest each time. Get that? Yeah. Okay. Any questions? Going too fast? Slow? No. So I think I'll just talk about one more thing, and because there's a couple more applications, but do you guys know about? You probably know about half-life, right? Half-life. Half-life they use in radioactive dating of old stuff. So half-life is how long it takes for usually a radioactive. It's not always radioactive. Radioactive elements to decay to half of its original amount. And and they use that a lot for figuring out how old stuff is, right? Because they'll look at like a dinosaur skeleton or something like that, and they'll see, oh, this carbon, whatever they use, carbon 14 or something, it has so much radioactivity in it compared to a new sample of that element, and then they can go back and figure out like how old like a dinosaur fossil is or something like that. Okay, I did some radioactive dating, but some of those girls were just too hot for me because they were radioactive, Okay, never mind. I've been married for a long time, so trying to make it dumb. So the formula for radioactive is like y equals a sub 0 1/2 raised to the t divided by h. They don't really have this formula in the book, but this would be the half-life. But this is at a sub 0. This is the half-life, and this is the original amount. Okay, so for example, in the book they have this one. It says the half-life of strontium. I didn't even know there was that. The half-life of. You guys know about strontium? Is there such an element? Strontium. I don't know. I never heard of that one. Okay, is 29 years, which is, I guess, a pretty short half-lives. Okay, 29 years. If the initial sample is 10 grams, how much will be left after 80 years? Okay, so the way you do that, you just plug into this plug into this formula, right? And so I guess we could call this A. This should be A instead of Y. A equals 10, right? 10 times 1/2 times 80 raised to the 80 over 29. So basically you're going through, what's that, 2 and about 3/4 half-lives, or 2 and a little bit, 2 and point something half-lives. So you're going to be multiplying 2, or 10 times 1/2 raised to the 2 point something. And if I, what would I get? What's the original amount? Oh, you already answered that question. But if I put in 0 in here, I'm always just going to get, what's 1/2 raised to the 0? 1, and so I'm going to get the amount in the original sample, right? So for this one, you just plug into your calculator. I'm not going to do it. And you get about, there would be about 1.48 grams left, okay? Now, you'll learn when we get to the solving logarithmic equations and exponential equations and stuff like that, how to find out the original amount given how much is in it at this time, right? So you'll learn how to go backwards, which you use using logarithms, and that's kind of it, okay? So have you done this stuff before, you guys? Yeah? Okay, so this should be relatively easy. And I did post this week's stuff on my website, so I didn't get to next week yet, but we're going to kind of buzz through this chapter pretty quick here. Chapter 3, so I've been trying to put the dates when we start, that's today. And so today I tried to be colorful too with this one, but maybe you can't see it. But yeah, look, can you see that? Maybe. There it is. I guess it's not such a big color. Page 189, 1 through 8, all that. And 81 through 84, you could do it with a calculator, but it's better kind of to think about it without a calculator. Okay? And that's that. And I'll stop and say goodbye. 32 minutes.